Download this code from codegive.com, link in the description below. Abusing bleeding-edge web standards for appsec glory, a deep dive with code examples. This tutorial explores how seemingly benign, or even beneficial, bleeding-edge web standards can be twisted, abused, and exploited to create novel and impactful web application security vulnerabilities. We'll go beyond traditional XSS and CSRF and delve into areas like service workers, bypassing cores, manipulating traffic, and persistent XSS. WebAssembly, wasm client-side exploitation, sandbox escapes, though extremely difficult, and bypassing security scanners. WebSockets, exploiting flaws in handshake logic and crafting malicious server-sent events. Web Bluetooth / web USB / web NFC * physical proximity attacks and device manipulation. Progressive web apps, PWAs, offline persistence vulnerabilities and manipulating application update mechanisms. Feature policy, permissions policy circumventing restrictions and enabling otherwise blocked functionalities. Disclaimer: the techniques described below are for educational purposes only. Do not attempt to use them against systems without explicit permission. Ethical hacking requires responsible disclosure and adherence to legal boundaries. Service workers, the undiscovered country of client-side vulnerabilities. Service workers, SWS, are JavaScript scripts that run in the background of a web browser, enabling features like offline functionality, push notifications, and background synchronization. Their persistent nature and the ability to intercept network requests make them a powerful tool for attackers. Cores bypass and request manipulation. SWS can intercept any network request originating from their registered origin. This allows them to effectively bypass cores, cross-origin resource sharing, restrictions. An attacker can register a SW on a compromised or attacker-controlled site, and then use that SW to make requests to any API endpoint, regardless of its core's policy. Example: one attacker controls attacker.com and registers a malicious service worker. 2 victim visits attacker.com. The SW is installed. 3 attacker crafts a malicious request to api.victim.com*. Because the SW intercepts the request, the core's policy of api.victim.com is circumvented. The attacker can now access and exfiltrate sensitive data. The mode, cores in the fetch call on the attacker page is important. It triggers the necessary cores pre-flight on the target server so the SW can observe the proper access control. Allow origin headers in the response. Mitigation ***. Scope service worker registration carefully. Ensure SWS are only registered for the minimal scope necessary. This reduces the attack surface. Use cores properly. While SWS can bypass cores, it doesn't mean you shouldn't implement cores. It still protects against many other attack vectors. Verify origin header. Implement server-side checks on the origin header to ensure requests are coming from legitimate origins, even if a SW is present. This provides an extra layer of defense. Content security policy, CSP restrict the sources from which the service worker script can be loaded. Use script src self, service worker src self. Be persistent XSS, service worker injection. If an attacker can inject JavaScript code into the SW's script, they effectively achieve persistent XSS. The malicious code will run in the background every time the user visits a page within the SW's scope. This is particularly dangerous because it affects all origins under the service worker scope. Example: One vulnerable application *. An application allows users to upload custom JavaScript code that gets used by the service worker. This is a terrible design choice. 2. Attacker injects malicious code *. The attacker injects the following code. 3. The service worker is updated, and the malicious activate event listener sends messages to all controlled tabs containing XSS*. Any page controlled by the SW will now receive the post message containing malicious code, leading to XSS when the application renders the message without proper sanitization. The eval example is even more dangerous. It allows arbitrary code execution within the service worker context. Mitigation *. Never allow user-supplied code in service workers *. This is the golden rule. Do not allow any external input to influence the service worker's code. Treat the service worker code as highly trusted. Input validation and sanitization, though not ideal if absolutely necessary, and it rarely is, rigorously validate and sanitize any input used within the service worker. However, avoiding user-supplied code entirely is a much safer approach. Code reviews *. Thoroughly review service worker code for potential vulnerabilities before deploying it to production. Sub-resource integrity *. Ensure the service worker script is loaded from a trusted source and hasn't been tampered with by using attributes on the script tag in your HTML. Denial of service (DOS). A malicious SW can intercept all network requests and either drop them or delay them indefinitely, effectively causing a DOS. Example *. This SW will intercept every fetch request and never return a response, effectively making the website unusable. Mitigation *. Implement timeouts *. Use timeouts within your fetch calls to prevent indefinite delays caused by a malfunctioning or malicious SW. Monitor service worker performance *. Track the performance of your service workers to identify potential issues like excessive CPU usage or memory leaks. Proper error handling *. Implement robust error handling in your service worker to gracefully handle unexpected errors or network failures. 2. WebAssembly, WASM, the binary frontier of client-side exploitation. WebAssembly, WASM, is a binary instruction format that allows near-native performance in web browsers. While WASM itself isn't inherently insecure, it introduces new avenues for exploitation. Bypassing security scanners *. Traditional JavaScript security scanners often struggle to analyze WASM code effectively. This can allow attackers to hide malicious logic within WASM modules and bypass detection. Example *. One attacker compiles malicious JavaScript code to WASM *. They use a tool like benign or mscripton to convert their JavaScript code into WASM. This code might contain XSS payloads, or malicious code to steal sensitive information. 2. Embeds the WASM module in a website *. Since the malicious code is compiled into WASM, many security scanners will fail to detect it, allowing the attacker to execute arbitrary code on the client's machine. Mitigation *. Use WASM security scanners *. Invest in WASM-aware security scanners that can analyze WASM modules for vulnerabilities. Monitor WASM usage *. Track the usage of WASM in your application and investigate any unusual or suspicious activity. Apply strong content security policy, CSP. Use CSP to restrict the sources from which WASM modules can be loaded. Use script src self-WASM unsafe eval. The WASM unsafe eval keyword is necessary because WebAssembly compilation effectively performs an eval operation. Runtime verification. Future research and implement runtime verification techniques to analyze WASM code during execution. This is an area of ongoing research. Client-side CPU exhaustion. DOS. WASM can be used to perform computationally intensive tasks. A malicious actor can leverage this capability to exhaust the client's CPU, leading to a denial of service. Example asterisk. The repeated execution of the computationally expensive Fibonacci function within the wasm module will quickly consume the client's CPU, leading to a DOS. The user's browser becomes unresponsive. Mitigation asterisk. Asterisk resource limits asterisk set resource limits on wasm execution using browser APIs or other sandboxing mechanisms. This is challenging, as browser controls are limited. Asterisk code reviews asterisk thoroughly review wasm modules for computationally intensive operations before deploying them to production. Asterisk monitor CPU usage asterisk monitor the CPU usage of your application to identify potential DOS attacks caused by wasm code. 3. WebSockets, the real-time communication vector. WebSockets provide persistent, bidirectional communication channels over a single TCP connection. They are often used for real-time applications like chat, gaming, and live data feeds. Vulnerabilities in WebSocket implementations can lead to various security issues. A handshake manipulation asterisk. The WebSocket handshake is the initial negotiation process between the client and the server. If the server doesn't properly validate the handshake, an attacker might be able to manipulate it to bypass authentication or perform other malicious actions. Example asterisk. One vulnerable server asterisk the server doesn't correctly validate the origin header in the WebSocket handshake. 2 attacker crafts a malicious handshake asterisk. If the server doesn't validate the origin header, the attacker can successfully establish a WebSocket connection with the server, even though the request originates from attacker.com, which is an unauthorized origin. This allows the attacker to impersonate a legitimate user and potentially access sensitive data. Mitigation asterisk. Asterisk strict handshake validation asterisk thoroughly validate all headers in the WebSocket handshake, including the origin, SCC WebSocket key, and SCC WebSocket version headers. Reject connections with invalid or suspicious headers. Asterisk use a secure WebSocket library asterisk employ well-vetted and regularly updated WebSocket libraries that handle handshake validation correctly. Asterisk implement authentication asterisk implement robust authentication mechanisms to verify the identity of clients connecting to the WebSocket server. B server sent events, SSE, injection asterisk. Server sent events, SSE, are a one-way communication protocol where the server pushes data to the client. If the server doesn't properly sanitize data before sending it as an SSE, an attacker might be able to inject malicious code or data into the stream. Example asterisk. One vulnerable server asterisk the server echoes user-supplied input directly into the SSE stream without proper sanitization. 2 attacker crafts a malicious SSE request asterisk. The attacker includes script alert, XSS/script in the data parameter. The server echoes this into the SSE stream, and the browser executes the script, resulting in an XSS vulnerability. Mitigation asterisk. Asterisk sanitize SSE data asterisk thoroughly sanitize all data before sending it as an SSE. Encode HTML entities and prevent the injection of arbitrary code. Asterisk use a safe SSE library asterisk employ a well-vetted SSE library that provides built-in sanitization capabilities. Asterisk content security policy, CSP use CSP to restrict the sources from which scripts can be executed, mitigating the impact of XSS vulnerabilities. 4. Web Bluetooth/webusb/web NFC, bridging the physical and digital worlds. These APIs allow web applications to interact with nearby Bluetooth, USB, and NFC devices. While they offer exciting possibilities, they also introduce new security risks. A physical proximity attacks asterisk. An attacker within Bluetooth/USB/NFC range can potentially exploit vulnerabilities in these APIs to manipulate devices or steal sensitive information. Example, Web Bluetooth. One vulnerable device **. A Bluetooth-enabled device has a poorly secured service that allows writing to a configuration characteristic. 2. Attacker crafts a malicious web application **. If the victim visits this malicious website and has the vulnerable Bluetooth device nearby, the attacker could potentially overwrite the device's configuration, leading to device malfunction, data theft, or other security compromises. The user must consent to the connection to the Bluetooth device, but social engineering could be used to trick them into accepting. Mitigation **. Device security ** ensure that Bluetooth, USB, and NFC devices are properly secured with strong authentication and authorization mechanisms. User consent * always require explicit user consent before interacting with any nearby device. Origin verification * verify the origin of the web application attempting to connect to the device. Limited permissions * grant web applications only the minimal permissions necessary to perform their intended functions. Sandboxing * enforce strict sandboxing mechanisms to limit the capabilities of web applications interacting with physical devices. CSRF-like attacks, with physical interaction. While traditional CSRF relies on tricking the browser into making requests, Web Bluetooth/webusb/web NFC can be used to craft attacks that require physical interaction but still leverage a user's existing trust. Example, Web NFC. One vulnerable system ** a system uses NFC to authenticate users. Visiting a website containing malicious code allows rewriting the data on an NFC tag. 2. Attacker crafts a malicious web application **. If the user visits this malicious website and then presents their NFC tag to the reader, the attacker could potentially overwrite the tag with malicious data, allowing them to impersonate the user. Again, the browser will ask for permission to use NFC. Mitigation **. Secure device authentication ** implements strong authentication mechanisms on devices to prevent unauthorized access. User education ** educate users about the risks of connecting to untrusted websites and interacting with unknown devices. Require multi-factor authentication ** implement multi-factor authentication to add an extra layer of security. Origin restrictions ** implement strict origin restrictions to prevent unauthorized websites from interacting with devices. Progressive web apps, PWAs offline functionality, offline vulnerabilities. Progressive web apps, PWAs, are web applications that can be installed on a user's device and provide an app-like experience, including offline functionality. This offline capability introduces new security considerations. Offline persistence vulnerabilities *. PWAs can store data locally using various storage mechanisms like local storage, IndexedDB, and the Cache API. If this data is not properly protected, it can be vulnerable to theft or manipulation. Example *. One vulnerable PWA *. The PWA stores sensitive user data, example API keys, session tokens, in local storage without encryption. 2. Attacker gains access to local storage *. An attacker can exploit a cross-site scripting, XSS, vulnerability to access the local storage of the PWA, even in offline mode. Mitigation *. Encrypt sensitive data *. Encrypt all sensitive data stored locally using strong encryption algorithms. Use secure storage mechanisms. Consider using IndexedDB with appropriate encryption options instead of local storage for storing sensitive data. IndexedDB allows for more granular control over data access and security. Implement proper data sanitization. Sanitize all data before storing it locally to prevent XSS and other injection vulnerabilities. Clear data on logout. Clear all sensitive data from local storage when the user logs out. Application update manipulation. PWAs use service workers to manage application updates. If an attacker can manipulate the update process, they might be able to inject malicious code into the PWA or prevent legitimate updates from being applied. Example: one vulnerable PWA *. The PWA doesn't verify the integrity of the updated service worker script. 2. Attacker intercepts the update *. An attacker can use a man-in-the-middle (MITM) attack to intercept the updated service worker script and replace it with a malicious version. This is extremely difficult to achieve in practice, as browsers enforce strict security measures for service worker updates. However, in theory, if an attacker could somehow bypass these checks, they could inject malicious code into the PWA. For example, consider an open-source PWA project. An attacker may inject code into the repo and distribute it via a package manager, such as npm. Mitigation Sub-resource integrity. Use SRI to ensure that the service worker script is loaded from a trusted source and hasn't been tampered with. HTTPS serve your PWA over HTTPS to prevent MITM attacks. This is absolutely critical. Code signing. Future explore code signing mechanisms to verify the authenticity and integrity of the updated service worker script. This is an area of ongoing research. 6. Feature policy, permissions policy enforcing security boundaries that can be circumvented. Feature policy, now called permissions policy, allows web developers to control which browser features are available to a web application. While it's intended to enhance security, vulnerabilities can arise if not implemented and understood correctly. Circumventing feature restrictions through iframes *. If a feature policy is not properly applied to all iframes within a page, an attacker might be able to bypass restrictions by loading malicious code within an iframe. Example *. One vulnerable page *. A page disables the microphone using feature policy, microphone none, for the main document, but doesn't apply the policy to an iframe. 2. Attacker loads malicious code in iframe *. The attacker's iframe can still access the microphone because the feature policy only applies to the main document, not the iframe. The attacker can now record audio without the user's explicit consent. Mitigation *. Apply feature policy to all frames *. Ensure that feature policy is applied to all iframes within a page using the allow attribute or the permissions policy HTTP header. Use sandbox attribute *. Use the sandbox attribute on iframes to restrict their capabilities. Careful feature selection *. Carefully select the features to disable based on your application's requirements. Misconfiguration leading to feature exposure *. A misconfigured feature policy can inadvertently expose features that should be restricted, creating security vulnerabilities. Example *. One misconfigured policy *. A policy intends to restrict access to the geolocation API but uses an incorrect syntax. The incorrect syntax might be interpreted as allowing geolocation from the same origin, self, and not explicitly disabling it, allowing malicious code from the same origin to access the user's location. The browser might also default to the standard security model if the directive is invalid. Mitigation asterisk. Asterisk use correct syntax asterisk carefully review the syntax of your feature policy directives to ensure they are correct. Consult the official documentation. Asterisk test your policies asterisk thoroughly test your feature policy to ensure that it is working as intended. Use browser developer tools to inspect the applied policies. Asterisk least privilege principle asterisk apply the principle of least privilege when configuring feature policy, only enabling the features that are strictly necessary for your application. 7. Conclusion, a constant state of security evolution. The security landscape is constantly evolving, and new web standards introduce both opportunities and risks. By understanding how these technologies work and how they can be abused, we can build more secure web applications. Remember, asterisk stay updated asterisk keep abreast of the latest web standards and security best practices. Asterisk think like an attacker asterisk try to identify potential vulnerabilities in your application from an attacker's perspective. Asterisk layer your defenses asterisk implement multiple layers of security to mitigate the impact of any single vulnerability. Asterisk automated testing and scanning asterisk integrate automated security testing and scanning into your development workflow. Asterisk code reviews asterisk conduct thorough code reviews to identify potential security vulnerabilities. Asterisk user education asterisk educate users about the risks of connecting to untrusted websites and interacting with unknown devices. The information provided here is a starting point. Further research and experimentation are essential for developing a deep understanding of web application security in the context of bleeding-edge technologies. Be responsible, be ethical, and help make the web a safer place. Good luck.